In this lab, we are using the known motion of the orbit of a star around a black hole to find the unknown mass of the black hole. Using fundamental principles like Newton's second law and the universal law of gravitation, we are able to find the mass of the black hole. Before we begin our computational model, we have a few things that we know about our system. The star has a mass of 1.989 times 10 to the 30th kilograms and has the x and y coordinates of motion that we are given through the data in a CSV file. We also want our time step to be 1 day or 86,400 seconds. We also know the position of the black hole. We assume that the black hole is the only object exerting forces on our star. Here's the code where I input my known values of the star's mass, the gravitational constant, and delta t. I also set up a sphere representing the black hole so that it was easier to visualize the orbit around it in my model. Here is where I told my code to read the data provided in the CSV file. Below this is where the code uses this position data of the star to calculate the components of its velocity. The first part of my calculation loop uses the data and the equation for momentum to solve for initial and final momentum and change in velocity and momentum. The next part of my loop deals with the calculation of the net force. Newton's second law tells us that F net equals dp dt, or the change in momentum over the change in time. We find d mag p dt by dividing the final magnitude of momentum minus the initial magnitude of momentum over the change in time. To find dp dt parallel, we multiply this by the p hat vector, which is calculated above. We can then set this equal to the parallel component of the net force. We can find dp dt perpendicular by subtracting dp dt parallel from the total dp dt, because the two components add up to equal the total dp dt. We can then set this equal to F net perpendicular. Then we set up code to add arrows into our model, which will show the parallel and perpendicular components of net force and total net force as the star is orbiting around the black hole. Finally, here I add in the equation for the universal law of gravitation that has been manipulated to find the mass of the black hole into my code using values from my loop. I then have the model print out the value for the mass of the black hole after running my model. Now I am going to run my code. The black arrow shows F net parallel, which is causing a change in the speed of the star. The blue arrow shows F net perpendicular, which is causing a change in the direction of the star. The yellow arrow represents the total net force. The arrows are larger as the star is closer to the black hole because the forces are greater when the distance is smaller, which is supported by the gravitation equation. Because the larger r gets, the bigger the denominator is in your equation, while the numerator is constant. Here you can see that the mass of the black hole is printed to be about 3.5662 times 10 to the 31 kilograms. If a different black hole with an unknown mass was placed in the same location and the star had the same motion, the black hole would have to be the same mass as the one calculated in my lab, because none of the variables in the law of universal gravitation would change. We would have the same mass of the star, the same g, and the same vector between the star and the black hole. So when we would solve this equation for the mass of the black hole, we would get the same answer. In conclusion, this lab shows that we can use fundamental principles to not only predict the future motion of known objects, but they can also be used to find an unknown value for certain properties, like mass, within our system by using what we know about the motion.